lenses behave very similarly to mirrors, except instead of the principle of reflection, we know that they use refraction. So light is able to actually pass through and bend through lenses. So you can still take the same two equations for focal length, image distance, and object distance, and our equation for magnification. Um, but the only difference between mirrors and lenses is the way that we assign the positive and negatives for real and virtual are uh, flipped around. So values of d prime, image distance, and f, focal length, are going to be positive for distances behind the lens, so on the other side of the object, and they will be negative for distances in front of the lens. So just like it was with mirrors, the image, or the object distance, sorry, is always still going to be positive. That's always where we're starting, so we always say that's in front of the lens. So lenses, both concave and convex, rely on refraction to focus light. The principle of dispersion that we talked about a little while ago tells us that there's actually a limit on how accurately a lens can focus light. So if you design a convex lens so that red light is focused exactly where you want it to be, then you've thrown off the ability to focus the violet light exactly in the same spot. So since it refracts differently, you can't ever get all visible wavelengths to be focused perfectly. First type of lens that we're going to talk about is the convex lens. So convex lens is some kind of transparent material that bulges in the center. So it's thicker in the middle than it is on the top and bottom. Lenses are designed to take all the light waves that pass through and focus them into one point. So focus light rays into the focal point. If you've ever seen in a movie or on TV someone burning ants with a magnifying glass, that's kind of what is going on here. Magnifying glass would be made from a convex lens, and they take all the light rays from the sun, focus them into a point. If you get it just right, you could burn up an ant, I guess. I never tried it. It seems cruel. So because convex lenses focus light into a single point, you might sometimes hear them called converging lenses. They bring all the light together to one point. It converges at the focal point. So all the terminology regarding lenses is the same stuff that we talked about when we were using mirrors. Lenses have a vertex, a principal axis, a focal point. Everything that was there before is still around now. So one new thing that we're running into with convex lenses and how they're different from concave mirrors is that if we had an object on the left side, for a mirror, the focal point was also on the left side. But for a lens, it's actually on the opposite side. So focal point, oh, I guess let's make it sound like grammar-ish. The focal point is on the opposite side of the lens. So for a lens, a focal point or a focal length greater than 0, then the equations that we talked about earlier. All right, let me try that again. I think I had a little mini stroke or something. So for a lens, our focal length is greater than 0. So the two equations can still apply. They applied to mirrors and they'll apply still to lenses because we said this is positive. We also want to take note that a ray of light passes through the vertex and it can go straight through without getting refracted at all. So if it comes in parallel, it still refracts down into the focal point. If it comes in through the vertex, it's able to pass straight through. And that'll be important a little bit later on when we're doing the ray diagrams with lenses. So you can see an example here in this diagram. We have the boy standing far enough away from the lens that his distance is greater than the focal length of the lens. So he's standing outside the focal length. So as we can see, this image is real. It's made from the actual rays that get refracted as they pass through the lens. So on the opposite side for a lens means real. So our image distance is going to be positive. So because that happens, then the image appears upside down. So the image height and magnification are both negative. If the boy were to step forward so that he is inside the focal length, the image changes pretty drastically. You can see what happens here. So now the image is virtual because it's on the same side as him. So our D prime distance to the image is negative. So that makes the image appear upright with image height and magnification both being positive. And you'll get some practice with lens diagrams.